Good morning. I am Dr. HEMALATHA, working as an associate professor in the Department of Computer Science and Engineering. So in this second part of my video lecture, I am going to cover on the topic theoretical issues in distributed systems. So the books which I have referred for preparing this presentation, and some of the presentation slides I have taken from the sources of Operating Systems by Dhananjay Damdir, and next is Advanced Operating Systems by Shingal Shivaratri. The agenda of my today's video lecture is, first we will see what is distributed system, and next distributed computing, and the global state is going to be a biggest issue in distributed systems. So my focus in this lecture is how to record the state of a processes that is running in a distributed computing environment in a consistent manner, for which we need to understand the time, state, and the corresponding states and the events in a distributed system. And whenever if an event is happening in any part of our distributed computing environment, at which time it is being recorded or at which time it is being happened has to be recorded, so that we could able to arrange the events in a strictly sequential order or partial ordering. So time, clocks and event precedence has to be considered. Then recording, finally the recording of the state of a distributed systems will be seen today. Then the global state and local state capturing algorithms I'll be touching here. Then the corresponding challenges and the algorithms. Fine. So first we will see what is a distributed system. A distributed system is a collection of sequential processes which is denoted by P1, P2, P3, etc. till Pn, where each and every process executes in a different parts of a system in a network, where all the systems collectively together to form a distributed computing environment. So here the ultimate requirement behind the distributed computing environment formation is we are in need of a strong, robust network. So a network is capable of implementing communication between the processes that is running in different machines, which has to communicate each other using message passes, message exchanges. Next, there are some assumptions which we need to take while doing anything under distributed computing environment. So here we are taking the channels are reliable, but the delivery of messages will happen in out of order. So the first message may be received later than the second message. So that we call it as out of order. Then every process can communicate with every other processes, may be directly or may not be. Then there is no reasoning based on the global clocks. The distributed computing environment has the absence of global clock. So that is the reason why we have to work on other way of communicating between the processes by using logical clocks. So the distributed computation is a distributed program, a program that is going to be executed in several systems that is connected to a network, and that is going to collectively work together to get the output of a program of a problem. So here a distributed program is executed by a collection of processes in a distributed computing environment where we need the network. Then each process executes, every process will execute a set of events where we can classify the events into two types. One is correlated or related or unrelated. So related events has to be ordered, and concurrent events need not be ordered. So we require the partial ordering. Then the communication between the processes will happen through message passing. So the basic two primitives that we use for communicating between the processes are send primitive and receive primitive, where M is the message identifier. We will see in detail how it is being done. So coming to the distributed computation definition. So distributed computation is a single execution of a distributed program by a collection of processes. So collection of processes means we are going to execute a single process in a single machine. Likewise, several such processes are going to be executed in a set of machines that's going to take care of handling a task. Finally, the outcome of the end of the execution of all the processes will be the final result. So each sequential process generates sequence of events that are either internal events or communication events. So generally every operation we call it as an event, but with respect to a distributed computing environment, any operation that happens within the process which does not affect the other processes, we call it as internal event. Or if a process is going to send a message, through that message the other process is going to get affected, or it has to take this message into consideration and do something related to the previous message. We call that as communication events. So the local history and the global history is most needed in order to record the global state of a distributed computing environment. The first thing is, what is local history? So here the local history of process Pi. So every process is denoted with a letter P, and I is the name of the process. So the local history of process Pi during a computation is a sequence of events that can be denoted as Hi, where Hi constitutes of sequence of events EI1, EI2, EI3, etc. till EIN. So if n set of events are going to happen within a process, we can able to collect the local history of any process by recording each and every event, whether it's going to be a related unrelated event or related event, means concurrent event or a causally related event. We will see what is concurrent event and causally related event in future slides. Then a partial local history of a process is a prefix of the local history. So every time whenever we record the local history, we may not be sure whether it is complete or incomplete. So whenever we do the recording of the state, it may be complete or it may not be complete. So we can divide the history into partial and complete, as well global history and local history. So partial local history of a process is a prefix of the local history. So that is Hi of n, that contains sequence of events EI1, EI2, etc. till EIN. The global history of a computation is the union of all the processes that is executing cooperatively to carry out a task in order to get the desired result. So that is denoted with a set H, which is union of set of processes running from 1 to n. So P1 to P2, P1 to Pn, and all the local histories. So H1 is the local history of process P1, H2 is the local history of process P2. Likewise, we have to collectively collect all the local histories of the different cooperating processes, and we have to record the global history. So what actually this global history will convey to the users? Certainly. So it is just the collection of events that have occurred in a system to carry out a task, and it does not give us any idea about the relative times between the events. So when it was happened and whether it is a overlapping or non-overlapping cannot be known through this, as there is no notion of global time because the global clock is missing. So the absence of global clock leads to a lot of issues in creating a coherent or consistent state for a distributed computing environment for a computation. So then the events can only be ordered based on the notion of cause and its effect. So we need to identify which are all the concurrent events and which are all the causally related events. So the concurrent events need not be given focus, but the causally related events must be strictly sequential. So let's formalize this idea. First we will see what is the notion of time and state with respect to a distributed computation. So here the time indicates when an event has occurred in a distributed computing environment in a node. Next, the state of an entity. Entity refers to a machines that is involved for carrying out the distributed computation, which is in which the process is being executed. So the state of an entity is the condition or mode of its being. Currently the state of the condition or mode of its being. So that depends on the several features. So the global state of a system comprises the states of all entities in a system, particularly to a specific instant of a time. Next, OS uses the notion of, particularly the operating system uses the time and state for performing the scheduling of resources and the CPU. So we need the chronological order in which the request occurred, and based on the chronological order every machine has to allocate resources accordingly. Then distributed OS uses them for recovery too. Based on the order of execution, whenever it has to recover back, the same thing has to be rolled as per the, so here we need strictly sequential order. The problem is fine, so we have identified the absence of global clock is the main problem in distributed systems to arrive at a solution for this issue. So the states are divided into local states and global states. Let me come to the point clearly. What the local state is, whenever if a process is executing in a system, that is a part of a distributed computing environment, we need to identify the sequence of events that is happened within a process, and that we call it as local state. So all the set of events that is happened within a process between the duration of the lifetime of the process, we call it as a local state. Likewise, set of processes P1 to Pn will cooperatively carry out a global task, and that we call it as all the states of individual process must be collected, and we need to construct a global state, that we call it as a global state. Now coming to the point of events, so the events are, everything is an event, even reading a variable, writing a variable, or reading something from a memory, or reading something from some other message, everything is or performing any operation within a process, everything is an event. But we can divide the events into two types. One is concurrent event, another one is happen before event. Concurrent events, we need not strictly follow the strict ordering for concurrent events, but if it is a happen before event, any event that has happened before must come in the same order than the other one. So the concurrent events, again we can divide into independent events and dependent events. For example, if E1 in process 1 and E2 are totally independent, that it doesn't have any common global variable, then we can say it is an independent event. But in case if the event E1 and E2 is going to access a global variable, we can say that those two events that is happening within the process P1 is dependent. Then coming to the next type of event, happen before events. So the distributed computing environment do bother only the happen before events, but not the concurrent events. So we need to preserve the ordering. Strict ordering should be preserved at least for happen before ordering, happen before events, but not for all. Means strict ordering cannot be applied in distributed computing event for the concurrent events and the happen before events. So let me come to the point, what has happened before events. So here happen before event is denoted by the symbol right arrow, that is, which means happened before, something has happened before the next one. So this is an example, A happened before B. So means A is some event that must be happened before the occurrence of event B. So it implies event A is happened before B. So that may happen within a process or between two processes. So whenever if two processes are cooperating together, so A can be the message sending event and B can be the message receiving event. So we'll see what has happened before relation with respect to the two different events in same process, or two different processes and two different events in different processes. So if A and B are events in the same process, then A happened before B, means A has an impact in the occurrence of B, or B has the impact in the occurrence of A. If A is the sending of message M by a process Pi, and B is the corresponding receive event by process Pj, then A happened before B, means without the process of message sending event, there is no meaning in message receiving event. So that's why message sending event must be recorded before the message receiving event in the global state. Then finally, coming to the transitive property of the relation, happen before relation, if A happens before B and B happens before C, then that implies A must have happened before C. Then if A does not happen before B and B does not happen before A, then A and B are the events, we call it as concurrent events. So in which A does not affect A does not affect the occurrence of B, or B is not influenced by A. Then this relation defines a partial order. So partial ordering is sufficient to preserve the consistency of a distributed computation, but not the strictly sequential. So on the whole, we can have the space-time diagram. So this is particularly the space-time diagram for three processes running together for a computation, for carrying out a computation in a distributed computing environment, in which three processes are happening concurrently, and process P1 has several events which we denote as E11, E12. So E1 specifies that the events are happened for P1, here it is E2, here it is E3. But the different events that has happened in process P1 is denoted as 1, 2, 3, 4, 5, 6. since we are talking about the event, we use the same symbol E as a notation here. So the process P1 has several events, P2 has several events, P3 has several events. If you look at the diagram, the time starts here, that is at t is equal to 0, your process is being executed. But sometime later, your process is generating a message where that is, say it is sending a message to process P3, right? And at the same time, sometime before, P2 is generating another message where it is using send of M from P2 to P1. And certainly after some time interval, the P3 is sending another message from P3 to P1. So if you look at E11 is influencing E23 and E21 is influencing E12. So E11 must have happened before E32 and E21 must have happened before E12. So the relations how we can define for this particular space-time diagram is E11 happens before E23, E12 is happened before E21. Likewise, E33 is happened before E31 and E41 is happened before E32. Here E43 is happened before E22. And if we look at E6 can be a concurrent event with respect to E5 for process P1. So this is a request message, and this is again a request message for which the process P3 is generating a response message back to process P1. So that is why we have denoted the keyword as rest above the edge. So then again P3 is sending a request message to process P2, and again this is a response message. Now P1 is generating another response message because previously it has received a request message from P2 at some time greater than the occurrence of event E11. Then it is generating a response message back to P2 after having this many causally related events. Then P3 is receiving a request message from P1, for which the P3 will be generating the reply messages, which is not shown in this slide. So graphical representation of a distributed system can be shown by using the space-time diagram. So if there is a path between two events, means they are related. So here the E11 and E23 are related, E21 and E21 and E12 is related, E33 and E13 is related, likewise E34 and E22 is related. So otherwise if there is a path, it means they are related. If there is no path, it means that is concurrent. Whether the notion of ordering is much important with respect to a distributed system, yes or no? Yes. So why? Because we need to order the events based on the occurrence of concurrent events and the causally related events. So for which we are in need of strict ordering. Because of the lack of global clock, we cannot able to go with a strict ordering of all the events that is happening in a distributed computation, but at least partial ordering must be attained for arranging all the events that is causally related to each other. So here some idea of ordering of events is fundamental to reason out how a system works. So we have to construct a global state for which the local states has to be recorded. From the local state, the machine has to construct the global state. So the global state detection is a fundamental problem in a distributed computing environment, where it has to enable the detecting stable properties of a system. When a machine do fail, or whenever if a machine is failing to perform a particular event or a particular operation in the process execution, has to be recorded. How do we get a snapshot of a system? So ultimately there comes we need to think about how do we take a snapshot of a system that is a part of a distributed computing environment when there is no notion of global clock or shared memory. Then the state collected must be consistent. That is the requirement of the outcome of a global state, but we are not sure whether the state what is collected recently is a consistent one or inconsistent. So these are all the issues that is related to the distributed computing in for ordering the events. Then we have to apply some alternate mechanisms in order to arrive at the consistent global state recording of a particular computation in a distributed computing environment. So first we will see how the local states and the global states can be recorded, and then we will look at some of the algorithms through which we can able to construct a consistent global state. So each entity, every entity that is a part of a distributed computing environment has got its own state, where the state consists of state of a memory cell and the corresponding value contained in the memory cell, then the state of the CPU, that is we need to know the PSW and the general purpose registers value. So the program status word and the general purpose registers content must also be recorded to have the state of a particular entity. Then the state of a process. We need to know whether currently the process is running or suspended or terminated. So the state of a memory allocated to it has to be recorded. CPU state, whether the current state of the process with respect to the status of a process, then state of inter-process communication must all be recorded in the state of a particular entity. So the state of an entity, we can call it as a local state, because that can take the snapshot of a local machine but not the other machines. So that's why we call it as a local state. The state of a process pk can be denoted as S of k at a time t. So at any point of time the snapshots will be recorded only at a particular time. So we need to consider the time into consideration for collecting the states of the local process as well as global process. So here the state of a process for pk at a time t is denoted as S denotes the state, t denotes the at a time t we are recording the state for the process pk. So global state, so that is the definition of the local state. Global state is the collection of all the local states of all the entities at the same instant of time, so which we call it as the global state of system at time t. S of t is comprises of union of S1 of t. So S1 of t denotes that is the local state recorded for process P1 at a time t. Likewise S2 of t, etc. till Sn of t. So if the computation comprises of processes P1 to Pn, we can say the local states S1 of t to Sn of t must be collected to construct a global state. So coming to the event, now we are going to concentrate on what is a concurrent event and what's a causally related event. So first we will see an event that can be sending or receiving a message. Sending a message is an event and receiving a message is an event. Performing an addition is an event, or doing a read is an event. Doing a write is also an event. So incrementing one to a variable or adding some value to another variable, everything is an event. So here the events what we are going to consider for recording the global state is only causally related events. So an event can be sending or receiving a message over a channel or other. So here other includes every other unrelated or concurrent events. So here whenever we say that is a channel is nothing but a communication fabric through which two machines can interact with each other. So an interprocess communication path. Then a process state changes whenever an event occurs in it. So here the event is represented as follows. What that is, first thing is process ID, the next is old state, the state before the execution of event E1, and the state that is captured after the execution of event E1, then the corresponding description of the event, then the channel state and the corresponding message. So this is how an event can be represented. So there may be other way in which the event can be recorded, that is based on the type of the algorithm and the machine, and the type of the distributed operating system in which we execute this algorithm. The channel and message are, you can, for example, the channel and message can be allowed with the null values if event does not involve sending or receiving of a message. For example, if an event is recorded but it is not either sending a message or receiving a message, so you can have hyphen or null value for channel and message. So here the process PK state can be denoted, the old state S and the new state is denoted as S dash. Particularly for a single process we are talking. So here for process PK, the old state of process PK is denoted as S, and after the occurrence of event EI, the state of the process is changed from S to S dash, so that is new state of PK. So here the change of state in process PK has happened because of the occurrence of event PK. So the process ID is PK, then the old state is S and the new state is S dash, and what is it doing? The process is sending a message. So that is happening within the process. So yes, send, that is event description is sending a message, and the channel is denoted as C and the message is identified as M. Now we have seen the events and what is actually local state and global state and the corresponding types of events. Now we'll come to the point of how the global clock is going to be replaced with the logical clocks in a distributed computing system. So global clock definition is, it's from the term it's very clear that it is going to be a global clock, and that's an abstract clock that can be accessed from different sites of a distributed computing systems with identical results. But the problem is, if the global clock is situated somewhere, there is a delay incurred between the machine that is contacting the global clock for getting the current time and recording the state. So there is a delay involved in communication, so that we call it as latency. So here it cannot be implemented in practice because that is, the communication delay is considerable and it should be included where there is no bound, because for the first time when we communicate with a universal time clock, the delay may be less or it can be negligible, so that you need not consider the delay into consideration while recording the event. But in case during the peak hours the delay is considerable, and again particularly where the universal time clock is located, again that is going to be an influencing factor. So the global clock do have the unbounded communication delay, that's why we are not considering the global clock for recording the global state. Then ultimately the other alternate to the absence of global clock is, we can go for logical local clocks. So the local clocks are going to be logical, where that is going to be preserved only for a machine and a process within a machine. So the local clocks should be reasonably well synchronized. So that's the requirement. Now we are going to look at what is event precedence and then the other relations between the events. So here event E1 is happened before E2 indicates event E1 precedes E2 in time. That is, event E1 has occurred before E2. So event ordering implies arranging set of events in a sequence such that all the event that precedes before the other events should come just like that, as it is how it is executed. So here event ordering implies arranging a set of events in a sequence such that each event in the sequence precedes the next one. A total ordering exists if all events that can occur in a system can be ordered, but this is impossible. But we can able to attain at least partial ordering with respect to causally related events. A partial order implies that some events be ordered, but not all events that has happened in different processes. So here a causal relationship is used to deduce precedences. So we can able to find out the precedence of two events based on the causal relationship. So here a message send event must precede the message receive event. So here we can say the event precedence can happen only for this kind of events. So the rules for ordering events in a distributed system is given here. We can categorize the event by happening, where it has happened and how it has happened. So events within a processes, events in different processes, then transitive precedence. As I said earlier, if A happens before B and B happens before C, then that implies A happens before C. So what is actually events within a process? The different operating system performs event handling in order to know which event has occurred within a process. So events in different processes. So in case if the events are not is going to be concurrent event, we need not focus much here. But again, if the event preserves the causal relationship, that is because of this event there is a change. So that's why we call it as cause and effect. Cause and effect relationship, an event that corresponds to the cause precedes an event in another process that corresponds to the effect. So because of this event, the other event, there is a change in the state. So that you call it as cause and effect. Cause is sending message, effect is after receiving the message, the particular process has to take care of something. So that's why we call it as cause and effect. So the transitive precedences, as I said earlier, E1 happened before E2 and E2 happened before E3. It implies E1 happened before E3. So EI precedes EJ, EI follows EJ. So we can able to define with the conditions if EK and EL exists such that EK has happened before EL and EI has happened before EK, or EI can be concurrent to EK and EL can happen before EJ, or EL can be concurrent to EJ. So it can be anything. So if it is within a process. If EI follows EJ, then this particularly if EG and EH exists such that EG must have happened before EH and EJ must have happened before EG. So or it can be EJ is concurrent to EG and EH has happened before EI, or EH must be concurrent to EI. So means EH and EI are not at all causally related, need not be causally related events, it can be concurrent events. EI is concurrent with EJ. If EI neither precedes nor follows EJ. When do we say that EI is concurrent with EJ? Yes, only if it doesn't precede or doesn't follow. Means if EI neither precedes nor follows EJ. Means EI doesn't happen before EJ or EJ doesn't follow EI. So that is the meaning of concurrent event and precedes and follows. So we have to take into consideration that precedes and follows should be strictly ordered while we construct the global state of an algorithm. So the timing diagram of has to plot all the activities of a different processes against a time. So here at a time t0 and here it may be time something t0 plus n, and at the end of the execution we could understand that it may be t0 to tn. So events in Pi are denoted as EI1, EI2. So that's why P1 is the name of the process. The first event in P1 is E11, second event in process P1 is E12, third event in the process P1 is E13. It is E21, E22, E23, E24. So likewise for P3 it is E31, E32. So for the nth process it is Pn1, for Pn it is En1, En2, etc. So here events in Pi are denoted as such. So E23, if we look at here, E23 is a message sending event which sends the message M1 to the process P1 through the communication channel. So here E23 is a message sending event for message M1 and E12 is the message receiving event. So we don't bother what has happened before E12 or E23 because E21, E22 is a concurrent event with respect to process P2 and P1 is E11, and when we consider on the whole E11 and E11 and E22 are the concurrent events with respect to the global state. Coming to the logical clock, so the time stamping must be done for each and every event that is happened within a process. We are going to use the logical clock value to record the global state and to arrange the events accordingly. So the clocks are loosely synchronized using causality. Means we are not following the logical clocks by using global clock value. Every machine that is going to be a part of a distributed computing environment has got its own logical clock. While utilizing this logical clock for carrying out a computation, If the logical clock value is going to influence the causally related event, we are going to apply the implementation rules based on the algorithm. So the implementation rules are IR1 can be denoted as IR1 and IR2. So here the algorithm for clock synchronization is when a process Pk would like to send a message M to process PL. So what Pk will do? Pk will execute a command send PL comma timestamp of message M, means at which time this message has been generated by Pk, then the message M, where TS of send of M is a timestamp uptime just prior to sending the message M. Then when the process PL receives such message M from process Pk, what it should do? It has to check the local clock of its own with the corresponding timestamp of the message what it is received. So means if it is less than this, the local clock of PL is less than timestamp of send of M. So what it has to do? It has to adjust the local clock by setting the local clock of PL is equal to timestamp of the message received plus delta. So this value is going to be assigned constant for process in a distributed computation. So here whenever if the local clock of the process that receives the message, whenever if it is less, it is going to add the corresponding timestamp at which the message is generated plus 1 or 2, or that's going to be decided by the algorithm. So the timestamp of that's going to be the timestamp of the receive event. Then local clock of PL is the value of the local clock of process PL, and a delta is the average communication delay in the network. So here in this algorithm we can able to compute this delta by taking the previous communication average. We can record all the previous communication delays and do average and smooth it, and then we can fix the delta value based on some thresholds. So here the logical clock LCK, so that is denoted as LCK is incremented by 1 only when an event occurs in process Pk. For example, here whenever if P1 executes set of events, then we are going to increment every time whenever an event is going to be occurred by 1. So initially all the logical clocks are initialized to 0, means here it is recorded as 9, 10, but the thing is previously there may be some events may be occurred or may not be occurred. So we can consider those events for recording the adjusting the logical clock value. So here a process Pk increments LCK by 1. So this is the rule. So rule 1 and rule 2. R1, what is rule 1 specifies is whenever a process Pk increments LCK by 1 whenever an event occurs, but we do not bother whether the event is a concurrent event or a causally related event. But R2, the next rule is whenever a process Pk receives a message M containing the timestamp message as well as some message from the other process, it has to set its clock by applying the rule the maximum, whether the local clock is maximum or the received timestamp message from the received timestamp value from the message, if either of these. So that is, this is the local clock of the process Pk, this is the timestamp of the message received from the sending process plus 1. So out of these two, whichever is maximum will be set for the local clock once after the message receiving event has happened. The condition is timestamp of EI is less than timestamp of EJ if EI has happened before EJ. Obviously, so whenever if a sending message has happened or later, the receiving message must be recorded. So the sending message time must be always lesser than the message receiving time. So that's why the condition must be preserved. Then the problem is if timestamp of EI is less than timestamp of EJ, the other way, again we could able to find out one more problem over here. Whenever if the timestamp of the previous event and the timestamp of the next event within between two processes, if it is less, it doesn't mean that they are causally related. It may be concurrent event. How do we create the unique timestamps? Is the logical time, again the two processes may set the logical clock with its own value at the same time, but the logical clock timestamps are not unique, so cannot be used to obtain the total order. because it's going to be only single value, scalar value. You cannot use that scalar value for adjusting the global clocks, for adjusting the total, for performing this total ordering across the total ordering of all the events in a distributed environment. So the problem can be overcome by using a pair. Pair is points, that is EI as the timestamp of EI, where point, that is local time comma process ID. So everywhere we are going to denote the occurrence of the event with the two values. One is the local time comma process ID. So then the events can be ordered as per the rule. So EI precedes EJ if and only if PTS of EI dot local time is less than PTS of EJ dot local time. So we are going to take the local time of every process and do the comparison if it is less than or if it is equal or the process ID. So the process ID can be, for example, the process ID can be, the single process can create the child process from which the different events might have happened. So we can take. So the second thing is if the local time is going to be equal for the two different events that happen for two different events EI and EJ, then the corresponding process ID must be ensured whether this process is lesser, process ID is lesser than the other process ID. So because of the problem, because of this kind of the local logical clock timestamps cannot be unique, we have to do all these things. So the drawback in this can be overcome by using the vector clocks. So the logical Lamport proposed this logical clock where it can convey the information about its local clock alone. So to overcome the problem, we are going with a vector clock. So the vector clock contains n elements. Again, whenever if n refers to the number of processes that is happening concurrently to carry out a computation in a distributed computing environment. So vector clock contains n elements, or I can say it's an n tuple, where each tuple contains n values, where n is the number of processes in the distributed systems. So again, for defining set of values for a single value, we have to go with a array. So here VC stands for vector clock for process K, contains K where the logical clock of process Pk. Again, VCK of L comma L is not equal to K, the highest value in the logical process of clock of process PL, which is known to process Pk. So we have to take the highest value across all the processes. For example, VCK of K alone will be influenced by its logical clock, but other clock values must be changed or updated whenever there is a causally related event that has happened with the corresponding process that is running in a distributed computing environment. So here we have to apply the other two rules. Rule 3, a process Pk increments VCK of K by 1 whenever an event occurs in it. So it can be a local event and it can also be a concurrent event. As well as if it is going to be a send message event, it has to increment by 1. Then by R4 is whenever a process Pk receives a message M containing the corresponding vector clock of the process that generates this message, then it has to set its clock by taking the maximum of the local clock and the message in the time that is attached to the message plus 1. So the precedence rule, if EI precedes PJ for all L, right, for every time the vector is going to be shared along with the messages in the timestamp as a timestamp. So when n, let's take, there are 3 processes. So the vector clock will have 3 values. The first value denotes the current clock value for the process P1. Second clock value denotes for the second process. Third clock value denotes the time clock for the process P3. So here you have to adjust all the clock values correspondingly based on the timestamp which it is received in the message receive event. So for all L denotes the number of processes that is communicating or cooperatively working together to carry out a task. So vector clock value of EI of L if it is less than vector clock value of EJ of L, and every time we need to ensure that it is not equal to. but it may not be equal. Sometimes it will be lesser or it will be greater. So the greater has to be taken into consideration and we need to adjust it. And EI follows EJ. So for all it will be greater. So this is opposite to it. So this is here we always ensure if EI precedes EJ, all the clock values in EJ in EI must be lesser than EJ. But here all clock values in EI must be greater than EJ. So we need to adjust it accordingly. So if EI and EJ are concurrent, we need not ensure this. So it can be less than or it can be greater than. So here the VTS of, that is vector timestamp, vector clock timestamp value of EI is less than vector clock timestamp of EJ if and only if event EI is happened before EJ. So synchronization of vector clocks. So as I said, we have 3 processes. So each and every value will have each and every value that is recorded in process for every event with the timestamp is 10, 0, 0. So since 9 events must be happened before the occurrence of this E11. So we are recording the timestamp as 10. This is for process P1. But previously, if you look at all the process P1 might not have communicated with P2 and P3, so the other 2 values are 0 initially because it doesn't know the clock value of P2 and P3. So here P1 might have occurred, 9 set of events might have occurred at P1, so it is incremented to 10 because of the occurrence of the event E11. So 10, 0 doesn't know about the clock value of P2 and P3. So it is generating the message M1 to process P2. So process P2 will receive a message where it is 10, 0, 0, M1. So it has to apply the rules, that is R3 and R4, and it has to adjust it. So here again if you look at the process P2, the process P2's clock value is denoted as the second value in the tuple. So here this is 10 is received from P1, so it has to apply rule 1, which is higher has to be taken here. So previously here it might have been 0, 0 is compared with 10, since 10 is larger it has to record 10 here instead of having 0. Then here it is 0, here it is 4, so 4 has to be recorded here and again 0, 0, so can be kept as it is. Then after this the second event is happening at P2 where it is going to affect P3. So E22 is the second event that is happening at P2, which we call it as a causally related event because it is going to send the message M2. So M22 process P3. So this has happened after the occurrence of this event, or E21 has happened before E22. So E22 has to attach the timestamp as 10, 4, 0 to it to process P3. So previously there may be something else. So here 10, something else that has happened in P3. So thereby 24 set of events might have been happened. So according to the vector clock IR1, it is incremented to 25 on receiving this message event. So, and the corresponding clock values have been set accordingly from the message what it receives from P2, that is 10, 4, 25. Then the next message that is generated after receiving the message from P2 is E32. So if we look at 10, 10, 4, 4. But since these two things cannot be adjusted because it is the clock value of the other two process, it has to adjust the local clock value because there is another event that's going to happen after this. So 25 plus 1, 26. So this is going to be sent to the process P1. So the process P1, what it has to do, it has to adjust its own clock value because after this event, only the next event is message receiving event. So 10 plus 1, 11, then 4 is message, that is 4 is the timestamp of the process P2 and 26 is the timestamp of the process P3. It has to record as it is. Then after this it is going to send another message for which only the 11 is incremented to 12, but it doesn't touch the timestamp for the process P2 and process P3. So 12 comma 4 comma 26. So let's come to the point of here. But when we analyze the process P2, after the occurrence of event E21, E23 has happened. Sorry, E22 after the occurrence of E22, E23 has happened, in which if you look at the 10 cannot be touched, but the 4 has to be incremented because that is the local time value of the process P2. So that is incremented from 4 to 5, but the other is kept as it is. Then after receiving this message from P1, it is adjusting the time values of the other clocks as well as its own local clock, where the message in which 12 is greater than 10, so it is changing from 10 to 12, and 4 is actually its own local clock. It doesn't take the local clock from others' values, so it adjusts its own value clock by adding 1 to it. Then 26 is compared with 0, so it is adjusting to 26. And this is how it's been recorded by using this vector clock. So now coming to the recording state of a distributed system. So it is not possible to get all nodes to record their state at the same instant or at the same time. So the local clocks as well are not perfectly synchronized, and again the collections of all the local states may be inconsistent or may not be consistent. So the alternate is we need to go with an algorithm where the different local states have to be collected and ensure that the global state is consistent or not. So let's come to a real-time problem where we have an issue in recording the global state in a distributed system. So inconsistent state recording. So let's take a banking application where the banking application is running across different sites, where let us take some amount of rupees is going to be transferred from account A to account B. So here let's take the banking application is happening in two different sites. One is node 1 in site S1 and node 2 in site S2. So let's denote the process P1. That is process P1 is the P1 is the process that is executing in node 1, and P2 is the process that is executing in node 2. And we are going to take the fund transferring system. For example, the process P1 is going to debit $100 from account A in node N1, and the $100 must be deposited in the account B, which is running at the site N2. So P1 sends a message to P2 to credit $100 to account B, and P2 credits the $100 to account B in node 2. So these three are the events that should happen one after the other, and the same thing must be shown in the global state recording algorithm. So if this will be record at the time of recording, if something is there in the transit, so here it is debited from 900 to 800, but that might not have been recorded at a site N2, that is it will be recorded as 300 instead of 400. So it leads to, when we add together 900 plus 300, it should be 1200, but instead it will be 800 plus 300, it will be 1100, where the state is inconsistent. So this leads to the problem. Inconsistent if A's balance is recorded before 1. So here before the occurrence of the event 1 or action 1, if A's balance is recorded and B's balance is recorded after 3, so that results the inconsistent state of the global state algorithm. So the consistent state recording can be done by collecting the local states, then ensure whether the state that is collected leads to a consistent global state or not. So every message recorded as received from P1 in PK state is recorded as sent to PK in P1 PL state, and every message that is recorded from message received from PK in PL state must be recorded as sent to PL. So the properties of a consistent state recording algorithm. Here we have 4 processes, P1, P2, P3, P4, and we have 5 channels. Channel 2-1, connecting a channel that connects P4 and P2, channel 4-2, 4 and 3, channel 4-3. Then we have to consider the other 2 channels that is connecting P2 and P3 in both directions. So when we take here, we have 4 processes, P1, P2, P3, P4. So P1 has different events, P2 has different events. There are some events which are concurrent and there are some events which are causally related. So means P2 is sending a message from it to P1. So E22 and E22 is a message sending event and E12 is a message receiving event. So what is we are going to do is we are going to define a cut where when we do a cut it has to lead a consistent global state. But there is a chance that the cut can collect the state of can collect the snapshot of a distributed system to an inconsistent. For example, here TP1, TP2, TP3, TP4 is going to be a cut. Means this is the time at which the snapshot of the local states are going to be collected to record the global state. So here the message receiving event is recorded in P3, but the message sending event is not recorded at P4. Likewise, here if we take P1 and P2, message sending event and message receiving event has been recorded before the snapshot is taken, so not an issue. But here in P2 the message sending event is recorded, but P3 the message receiving event is not recorded, so it is also not an issue. But here when we come to P3 and P4, P4 does not send a message to P3 is not recorded, but P3 has recorded an event that it received a message from P4. So this leads to an inconsistency. So a cut is taken means that a collection of local states is recorded. So the definition of a cut of a system is the curve that connects the points in a timing diagram at which the states of the processes which is running cooperatively are recorded in increasing order by process number. So when we start from P1, we cannot start a cut from P2 or Pn. So the cut must start from P1 and it has to go up to Pn. So the global state is a n tuple of local states, one for each process. Cut is a subset of the global history that contains the initial prefix of each local state. Therefore, every cut is naturally a global state. The properties of a consistent state recording algorithm. Cut C represents a consisting state recording of a distributed system if future of cut is closed under the precedes relation or events. So here means we have three different cuts, C1, this is C1, this is C2 and C3. If we look at the C3 is inconsistent because the message receiving event is recorded but the message sending event is not recorded. And if we take C2, so here the message sending event is recorded, then the message receiving event is not recorded, so it can be a consistent cut. And if you look at the cut C1, here message sending, message receiving is not recorded, and here message sending is recorded, here message sending is recorded. So we can say that C1 and C2 can be a consistent cut, but C3 is totally inconsistent. So we are going to look at the algorithm for state recording. So the assumptions of the algorithm are first in first out. The channels are first in first out and it is a unidirectional, and every channel has unbounded message buffering capability. So the state of the process indicates that the message sent and message received by it. We are using a special message called marker message that is going to be sent to the process, and whenever we receive a marker message it has to record the marker and it has to start capturing the local state. So the process, any process, if it receives marker over all channels which is incident on it, what it should do, it has to record the state of a channel over which it received the marker. Then if it is the first marker received, it records its own state, or if it is again if it is the second time, if the marker is received, instead of recording its own state, it has to just forward the marker message to the neighboring processes. So the notations what is used is received of ij means the messages received by pj over the channel CHIJ, means the process PI is sending the message to PJ over the channel CIJ. Then the recorded received messages recorded as received in the state PJ. So here the Chandy-Lamport algorithm comes with the two kind of steps. So whenever a process PI initiates the state recording, first it has to record its own state and it has to generate the marker message, and it has to send a marker to all the outgoing channels whichever it is connected to it. Whenever if a process PJ receives a marker over any incoming channel of CIJ, the process PJ performs any one of the following actions. So if PJ had not received any marker earlier, what it should do? It has to record its own state, then record the state of the channel as empty. Clear? So I emphasize once again, your channel must be recorded as empty before you receive this marker. Once after you receive the marker, you have to record its own state by recording the state of the channel as empty. Then send the marker on each of the outgoing channel connected to it and start recording all the events that has happened after receiving the marker message. Otherwise, if it has not received marker earlier, we have to do these three things. If it has already received the marker earlier, it has to record the state of the channel as the set of messages that is received from other cooperating process. So this is on the whole, the operation of the Chandy-Lamport algorithm has been demonstrated with a small example. So the recorded state versus global state has been shown with a set of events. A recorded state that does not match any global status, we take no messages have been sent, message M21 has been received. So here for process P1, M21 message have been received but no messages have been sent. But P2 messages M21 has been sent but no messages has been received. Clear? So then P3, no messages have been sent, no messages have been sent or received for both P3 and P4. So let me come to the close of my video lecture of today's in my today's presentation. So the problem is, for whenever we work in a distributed computing environment, recording the global state is a challenging because of the absence of global clock. So the operating system uses the notion of time and state, local state and the global state. Local state refers to the state of an entity and global state is the collection of all the states that cooperatively run together to perform a task. Then precedence of events must be deduced properly by using the causal relation operation. Then some events that is concurrent, we need not worry upon that. So, and the local processes has to be set by using the logical clocks, where the vector clock is better than the Lamport logical clock. So using local clocks in processes, we have already seen the logical clocks and the vector clocks. So the logical clock has got its own drawback, and thereby the drawback in logical clock has been overcome in vector clock. We have to include the process IDs in timestamps for total ordering, but it is not possible to record the global state of a system in a single snapshot. So the Chandy-Lamport algorithm can obtain the consistent recording of the process states using the special message called marker message. So finally the Chandy-Lamport algorithm can be better than the other two options. Thank you.